Alright, next we're going to do the inverse transforms. And then this will lead us at where we're going to be able to solve a differential equation using Laplace transforms with, looking at the transforms of derivatives. So this is going to lead us into solving differential equations using Laplace transforms. So we're talking about inverse transforms and then transforms of derivatives in this section. So here we have the Laplace transform of f of t. We know that that's just going to be capital F of s because capital F denotes that we took the Laplace transform of the lower f. So if I want to do inverse, and if you remember anything about inverse from Algebra 1, Algebra 2, all your classes, you should know that, the x and the y's, they switch. The solutions and the solutions and the variables kind of, change places. And so if I have the inverse of a Laplace transform, usually it's the Laplace of f of t equals f of s. Well, the inverse of that would be the inverse Laplace of f of s is going to equal f of t, is which we have here. All right. So an example of that would be if I have a Laplace transform of 1 is equal to 1 over s, the inverse Laplace of 1 over s is going to be just 1. That's supposed to be a 1. That probably denotes that better. And then Laplace sine of 2, if that's, equal to 2 over s squared plus 4, the inverse Laplace of 2 over s squared plus 4 is equal to sine of 2t. So, again, I'm just going to go ahead and, basically we're just changing up page 3 and switching it with the inverses. So, the page 3 of the notes was the Laplace transform of 1 over s equals 1. I'm sorry, the Laplace transform of 1 is equal to 1 over s. The inverse Laplace transform of 1 over s is going to equal to 1. And so here you just have a chart of all the inverse transforms of some basic functions. So, example 1, we want to do the Laplace transform of negative 1, the inverse Laplace of 1 over s to the 4th. Well, this looks like it could be, judging from all those, it could be the n factorial over s to the n plus 1. So we got to figure out what n is. Well, it looks like n plus 1 is going to be 4 because that's the power with the denominator. So I'll say, okay, n plus 1 is 4. That means n is equal to 3. And so when I do the Laplace transform of 1 over s to the 4th, if I want it to look like this, I'm going to have to add the stuff in there. And so I should have an n factorial on the inside. So if I put that on the inside of the Laplace transform, I need to make sure that I also take it out. So it needed a 3 factorial, so I take out the 3 factorial. So I'm dividing by 3 factorial. And so the Laplace transform of 3 factorial over s to the 4th was just t cubed. That's the inverse Laplace of that. And then 1 over 3 factorial is just 1 over 6. And so there's my solution. All right. Same thing for example 2. I need to denote which one it looks like. Well, the inverse Laplace of 1 over s squared plus 5, s squared plus 5, and I have just a 1 on top. So it looks like this has to be sine and not cosine. The reason why it's sine and not cosine is, and if it was cosine, there'd have to be an s on top. And there's no way I can add that variable in there because it's a variable and we don't want to introduce a new variable. We don't mind introducing numbers. And so this is what it looks like. So I need to find k. Well, the only thing that looks like I have the value of k is 5. So k squared is equal to 5. So k would be the square root of 5. And so I need to add a square root of 5 in for that k. So when I do that, I have to plug it into the numerator. Well, now I also have to take it out by multiplying by 1 over the square root of 5. And so now that I've done that, when I look at this is just, sine. So sine of the square root of 5t, because k is square root of 5. And I cannot forget my constant, the coefficient that I have outside 1 over square root of 5. Now, again, the inverse Laplace is also linear, so I can break it up into parts that might make it a little bit easier. So instead of dealing with s plus 2 squared over s cubed, what I'll do is I'll go ahead and write the polynomial form of the numerator, s squared plus 4s plus 4, and take that over s cubed. Well, now what I can do is I can, do s squared over s cubed, get 1 over s, 4s over s cubed, 4 over s squared, and 4 over s cubed. And now I'm going to go ahead and pull out, what I can. And so I have the Laplace transform just 1 over s, which that's nice because that's just 1. The Laplace transform of 1 over s squared, but I had to pull that 4 out. All right, well, 1 over s squared, that's just t, so it's going to be 4 times t. And then plus, now I have 4, I pulled a 4 out, and I was left on the inside with a 1 over s cubed. So I needed a 2 there. Because that was s cubed and n plus 1 equals 3, so n had to be 2. So it's 2 factorial over s squared. So I get 4 over 2 factorial. 2 factorial is 2, 4 over 2 is just 2, and so this is what I'm left with for my Laplace transform, the answer to the inverse Laplace transform. So that's what f of t was. The inverse of the Laplace transform, and here I have 10s over s squared plus 16. What I can do here, I can just pull out the 10. If I pull out the 10, I'm just left with s over s squared plus 16. Because I have that s there, it tells me that it's cosine. And this is my k squared, so k has to be 4. So it's just 10 cosine 4t. So example 4, not too bad.